On the basis of their properties, all the elements can be divided into two main groups, metals and nonmetals. Both metals as well as nonmetals are used in our daily life. We also use a large number of compounds of metals and nonmetals. Before we go further and give the definitions of metals and nonmetals, we should know the meaning of some new terms such as malleable, ductile, and brittle. Malleable means which can be beaten with a hammer to form thin sheets, without breaking. Ductile means which can be stretched, or drawn, to form thin wires. And brittle means which breaks into pieces on hammering or stretching. Keeping these points in mind, we will now write the definitions of metals and nonmetals. Physical properties. Metals. The important physical properties of metals are: 1. Metals are lustrous, or shiny, and can be polished. The property of a metal of having a shining surface is called metallic luster. The shiny appearance of metals makes them useful in making jewelry and decoration pieces. For example, gold and silver are used for making jewelry because they are bright and shiny. The shiny appearance of metals makes them good reflectors of light. Silver metal is an excellent reflector of light. This is why it is used in making mirrors. Though metals are generally hard. Most of the metals are hard. But all the metals are not equally hard. The hardness varies from metal to metal. Most of the metals like iron, copper, aluminium, etc. are very hard. They cannot be cut with a knife. There are some exceptions. Sodium and potassium are soft metals which can be easily cut with a knife. Tin metals are malleable. The property which allows the metals to be hammered into thin sheets is called malleability. Malleability is an important characteristic property of metals. Most of the metals are malleable. Gold and silver metals are some of the best malleable metals. Aluminium and copper metals are also highly malleable metals. All these metals can be beaten with a hammer to form very thin sheets called foils. Metals are ductile. The metals such as copper, aluminium, magnesium, and iron are available in the form of wires. The property which allows the metals to be drawn into thin wires is called ductility. Ductility is another important characteristic property of metals. Most of the metals are ductile. But all the metals are not equally ductile. Some metals are more ductile than the others. Gold is the most ductile metal. Copper and aluminium metals are also very ductile and can be drawn into thin copper wires and aluminium wires. Metals are good conductors of heat. By saying that metals are good conductors of heat, we mean that metals allow heat to pass through them easily. We take a flat aluminium rod and fix some small iron nails on it with the help of wax. This rod is clamped to a stand. Let us heat the free end, left end, of the aluminium rod by keeping a burner below it. We will see that the iron nails attached to aluminium rod with wax start falling one by one. The nail attached nearest to the heated end of rod falls down first. And then the next ones fall. But the nail attached to the clamped end of the rod drops last of all. The burner is placed below the left end of aluminium rod. So, the left end of aluminium rod gets heated first. Now, the left end of aluminium rod is hot but the right end of rod is cold. So, heat now travels from the hotter left end of aluminium rod to its colder right end. As heat travels from the left side to the right side along the aluminium rod, it melts the wax which holds the nails. Due to this, the nails fall down one by one. Metals are good conductors of electricity. Saying that metals are good conductors of electricity, we mean that metals allow electricity to pass through them easily. We take a dry cell, a torch bulb fitted in a holder and some connecting wires, copper wires, with crocodile clips, and connect them to make an electric circuit. There is a gap between the ends of the crocodile clips A and B, so no current flows in the incomplete circuit and hence the bulb does not light up. Let us now insert a piece of aluminium foil between the ends of crocodile clips A and B. We will see that the bulb lights up at once. This means that the aluminium foil allows electric current to pass through it. This shows that aluminium metal conducts electric current. The electric wires that carry current in our homes have a covering of plastic such as polyvinyl chloride, PVC. Polyvinyl chloride is an insulator. It does not allow electric current to pass through it. The electric wires have a covering of an insulating material, like PVC, around them so that even if we happen to touch them, the current will not pass through our body and hence we will not get an electric shock. Metals are sonorous. Metals are sonorous. That is, metals make sound when hit with an object. Sonorous means capable of producing a deep or ringing sound. If we suspend a big piece of a metal and strike it with an object, we will find that it makes a ringing sound. And we say that the metal is sonorous. The property of metals of being sonorous is called sonorousness or sonority. It is due to the property of sonorousness or sonority that metals are used for making bells and strings, wires of musical instruments like sitar and violin. Non-metals. The physical properties of non-metals are just the opposite of the physical properties of metals. Non-metals are neither malleable nor ductile. Since non-metals are not malleable, they cannot be beaten with a hammer to form thin sheets. Again, since non-metals are not ductile, they cannot be stretched to form thin wires. Thus, solid non-metals can neither be hammered into thin sheets nor drawn into thin wires. Non-metals are brittle, which means that non-metals break into pieces when hammered or stretched. Non-metals do not conduct heat and electricity. Non-metals do not conduct heat and electricity because, unlike metals, they have no free electrons, which are necessary to conduct heat and electricity. For example, sulfur and phosphorus are non-metals which do not conduct heat and electricity. There is, however, one exception. Carbon, in the form of graphite, is the only non-metal which is a good conductor of electricity. Since graphite, which is an allotropic form of carbon, is a good conductor of electricity, it is used for making electrodes. Non-metals are not lustrous. They are dull. Non-metals do not have luster, which means that non-metals do not have a shining surface. The solid non-metals have a dull appearance. For example, sulfur and phosphorus are non-metals which have no luster, that is, they do not have a shining surface. They appear to be dull. There is, however, an exception. Iodine is a nonmetal having lustrous appearance. It has a shining surface, like that of metals. Nonmetals are generally soft, except diamond, which is an extremely hard nonmetal. Nonmetals are not strong. They are easily broken. For example, graphite is a nonmetal which is not strong. It has low strength. So, when a large weight is placed on a graphite sheet, it gets snapped. Nonmetals have comparatively low melting points and boiling points, except diamond, which is a nonmetal having a high melting point and boiling point. Chemical properties of metals. What happens when metals are burnt in air? Metals react with oxygen to form metal oxides. Metal oxides are basic in nature. Some of the metal oxides react with water to form alkalis. Metal oxides, being basic, turn red litmus solution blue. The vigor of reaction with oxygen depends on the chemical reactivity of metal. Some metals react with oxygen even at room temperature. Some react on heating, whereas still others react only on strong heating. Example: copper metal also does not burn in air even on strong heating. Copper reacts with the oxygen of air on prolonged heating to form a black substance, copper second oxide. Aluminium metal burns in air, on heating, to form aluminium oxide. Though most of the metal oxides are basic in nature, but some of the metal oxides show basic as well as acidic nature. Those metal oxides which show basic as well as acidic behavior are known as amphoteric oxides. Aluminium metal and zinc metal form amphoteric oxides. Thus, aluminium oxide and zinc oxide are amphoteric in nature, which show basic as well as acidic behavior. Amphoteric oxides react with both acids as well as bases to form salts and water. Aluminium oxide is an amphoteric oxide which reacts with acids as well as bases to form salt and water. In this reaction, aluminium oxide behaves as a basic oxide because it reacts with an acid to form salt and water. Aluminium oxide reacts with sodium hydroxide to form sodium aluminate, salt, and water. In this reaction, aluminium oxide behaves as an acidic oxide because it reacts with a base to form salt and water. Most of the metal oxides are insoluble in water. But some of the metal oxides dissolve in water to form alkalis. Sodium oxide and potassium oxide are the two metal oxides which are soluble in water. They dissolve in water to form alkalis. Sodium oxide is a basic oxide which reacts with water to form an alkali called sodium hydroxide. Due to the formation of sodium hydroxide alkali, a solution of sodium oxide in water turns red litmus to blue. Potassium oxide is also a basic oxide which reacts with water to form an alkali called potassium hydroxide. Due to the formation of potassium hydroxide alkali, a solution of potassium oxide in water turns red litmus to blue. What happens when metals react with water? Metals react with water to form a metal hydroxide, or metal oxide, and hydrogen gas. All the metals, however, do not react with water. The intensity of reaction of a metal with water depends on its chemical reactivity. When a metal reacts with water, cold water or hot water, then the products formed are metal hydroxide and hydrogen gas. Potassium reacts violently with cold water to form potassium hydroxide and hydrogen gas. The reaction of potassium metal with water is highly exothermic, heat-producing, due to which the hydrogen gas formed during the reaction catches fire immediately. Thus, potassium is a very, very reactive metal. Sodium reacts vigorously with cold water forming sodium hydroxide and hydrogen gas. Calcium reacts with cold water to form calcium hydroxide and hydrogen gas. The reaction of sodium metal with water is also highly exothermic, heat-producing, due to which the hydrogen gas formed during the reaction catches fire and burns, causing little explosions. Thus, sodium is also a very reactive metal. Calcium reacts with cold water to form calcium hydroxide and hydrogen gas. The heat produced in this reaction is less, which is not sufficient to burn the hydrogen gas which is formed. The piece of calcium metal starts floating in water because the bubbles of hydrogen gas formed during the reaction stick to its surface. The reaction of calcium metal with water is less violent. So, calcium is less reactive than sodium. Magnesium metal does not react with cold water. Magnesium reacts with hot water to form magnesium hydroxide and hydrogen. The piece of magnesium metal starts floating in water due to the bubbles of hydrogen gas sticking to its surface. Calcium reacts with cold water, but magnesium reacts only with hot water. This shows that magnesium is less reactive than calcium. Metals like aluminium, zinc and iron do not react with either cold water or hot water. They react with steam to form a metal oxide and hydrogen. What happens when metals react with acids? Metals usually displace hydrogen from dilute acids. Only the less reactive metals like copper, silver and gold do not displace hydrogen from dilute acids. When a metal reacts with a dilute acid, then a metal salt and hydrogen gas are formed. Magnesium reacts quite rapidly with dilute hydrochloric acid forming magnesium chloride and hydrogen gas. The reaction of magnesium with dilute hydrochloric acid is less vigorous than that of sodium, so magnesium is less reactive than sodium. Aluminium metal at first reacts slowly with dilute hydrochloric acid due to the presence of a tough protective layer of aluminium oxide on its surface. But when the thin, outer oxide layer gets dissolved in acid, then fresh aluminium metal is exposed, which reacts rapidly with dilute hydrochloric acid. Thus, aluminium metal reacts rapidly with dilute hydrochloric acid to form aluminium chloride and hydrogen gas. Zinc reacts with dilute hydrochloric acid to give zinc chloride and hydrogen gas, but the reaction is less rapid than that of aluminium. Iron reacts slowly with cold dilute hydrochloric acid to give iron second chloride and hydrogen gas. All those metals which are more reactive than hydrogen, that is, those metals which lose electrons more easily than hydrogen, displace hydrogen from dilute acids to produce hydrogen gas. This is due to the fact that the more reactive metals give electrons easily, and these electrons reduce the hydrogen ions of acids to hydrogen gas. The metals like copper and silver, which are less reactive than hydrogen, do not displace hydrogen from dilute acids. Because they do not give out electrons required for the reduction of hydrogen ions present in acids. Thus, all the metals which are above hydrogen in the activity series displace hydrogen from dilute acids. Those metals which are below hydrogen in the activity series do not displace hydrogen from dilute acids. How do metals react with solutions of other metal salts? When a more reactive metal is put in the salt solution of a less reactive metal, then the more reactive metal pushes out the less reactive metal from its salt solution. In other words, a more reactive metal displaces a less reactive metal from its salt solution. The more reactive metal takes the place of less reactive metal and forms its own salt solution. For example, if metal A is more reactive than metal B, then metal A will displace metal B from its salt solution to form salt solution of metal A, and metal B will be set free. That is, salt solution of metal B plus metal A, salt solution of metal A plus metal B. When a strip of iron metal, or iron nail, is placed in copper sulfate solution, then the blue color of copper sulfate solution fades gradually and red-brown copper metal is formed. The copper metal produced in this reaction forms a red-brown layer on the iron strip. In this reaction, iron is displacing copper from copper sulfate solution. This displacement occurs because iron is more reactive than copper. If, however, a strip of copper metal is placed in iron to Nd sulfate solution, then no reaction occurs. This is because copper is less reactive than iron and hence cannot displace iron from iron second sulfate solution. Aqua-Regia. Aqua-Regia is a freshly prepared mixture of 1 part of concentrated nitric acid and 3 parts of concentrated hydrochloric acid. Thus, the ratio of concentrated nitric acid and concentrated hydrochloric acid in Aqua-Regia is 1:3. Aqua-Regia is a highly corrosive, fuming liquid. Aqua-Regia can dissolve all metals. For example, Aqua-Regia can dissolve even gold and platinum metals, though concentrated nitric acid or concentrated hydrochloric acid alone cannot dissolve gold or platinum metals. The reactivity series. Some metals are chemically very reactive whereas others are less reactive or unreactive. For example, potassium and sodium react very rapidly with cold water, so they are very reactive metals. Zinc and iron react only with steam, so they are less reactive metals. On the other hand, copper and silver do not react even with steam, so they are quite unreactive metals. On the basis of vigor of reactions of various metals with oxygen, water and acids, as well as displacement reactions, the metals have been arranged in a group or series according to their chemical reactivity. The arrangement of metals in a vertical column in the order of decreasing reactivities is called reactivity series of metals or activity series of metals. In reactivity series, the most reactive metal is placed at the top whereas the least reactive metal is placed at the bottom. Potassium is the most reactive metal here, so it has been placed at the top in the reactivity series. As we come down in the series, the chemical reactivity of metals decreases. Gold, being least reactive metal, has been placed at the bottom in the series. Since the metals placed at the bottom of the reactivity series, like silver and gold, are less reactive, so they are usually found in free state, native state, in nature. Though hydrogen is not a metal, but even then it has been placed in the reactivity series of metals. This is due to the fact that, like metals, hydrogen also loses electrons and forms positive ions. Properties of ionic compounds. The compounds containing ionic bonds are known as ionic compounds. They are formed by the transfer of electrons from one atom to another. The ionic compounds are made up of positively charged ions and negatively charged ions. That is, the ionic compounds consist of ions and not molecules. The important properties of ionic compounds are: ionic compounds are usually crystalline solids. For example, sodium chloride is a crystalline solid. The ionic compounds are solids because their oppositely charged ions attract one another strongly and form a regular crystal structure. The crystals of ionic compounds are hard and brittle. Ionic compounds have high melting points and high boiling points. The ionic compounds are made up of positive and negative ions. There is a strong force of attraction between the oppositely charged ions, so a lot of heat energy is required to break this force of attraction and melt or boil the ionic compound. Due to this, ionic compounds have high melting points and high boiling points. Ionic compounds are usually soluble in water but insoluble in organic solvents like ether, acetone, alcohol, benzene, kerosene, carbon disulfide, and carbon tetrachloride. The ionic compounds dissolve in water because water has a high dielectric constant, due to which it weakens the attraction between the ions. Ionic compounds conduct electricity when dissolved in water or when melted. This means that ionic compounds are electrolytes. Ionic compounds conduct electricity because they contain charged particles called ions. Although solid ionic compounds are made up of ions, but they do not conduct electric current in the solid state. This is due to the fact that in the solid ionic compound, the ions are held together in fixed positions by strong electrostatic forces and cannot move freely. So, solid ionic compounds are non-conductors of electricity. When we dissolve the ionic solid in water or melt it, the crystal structure is broken down and ions become free to move and conduct electricity. Thus, an aqueous solution of an ionic compound conducts electricity because there are plenty of free ions in the solution which are able to conduct electric current. Occurrence of metals. The natural materials in which the metals or their compounds are found in earth are called minerals. Some minerals may contain a large percentage of metal whereas others may contain only a small percentage of the metal. Some minerals may not contain any objectionable impurities whereas others may contain objectionable impurities which hamper the extraction of metals. Thus, all the minerals cannot be used to extract metals. Those minerals from which the metals can be extracted conveniently and profitably are called ores. An ore contains a good percentage of metal and there are no objectionable impurities in it. Thus, all the ores are minerals, but all the minerals are not ores. Extraction of metals. To obtain a metal from its ore is called the extraction of metal. The ores are converted into free metals by a number of steps which depend on the type of the ore used, nature of the impurities present, and reactivity of the metal to be extracted. The various processes involved in the extraction of metals from their ores and refining are known as metallurgy. The three major steps involved in the extraction of a metal from its ore are: concentration of ore, or enrichment of ore, conversion of concentrated ore into metal, and refining, purification, of impure metal. Enrichment of ores. The unwanted impurities like sand, rocky material, earthy particles, limestone, mica, etc., present in an ore are called gangue. Before extracting the metal from an ore, it is necessary to remove these impurities. The methods used for removing gangue from ore depend on some difference in the physical properties or chemical properties of the ore and gangue. By removing the gangue, we get a concentrated ore containing a much higher percentage of the metal. Extracting metals low in the reactivity series. The less reactive metals such as mercury and copper, etc., are placed quite low in the reactivity series. So, the extraction of less reactive metals means the extraction of metals which are quite low in the reactivity series. The less reactive metals which are quite low in the activity series are extracted by the reduction of their oxides by heat alone. Mercury is a less reactive metal which is quite low in the activity series. Mercury metal can be extracted just by heating its sulfide ore in air. Mercury metal is produced from the sulfide ore called cinnabar, HGS, which is actually mercury though Nd sulfide. The concentrated mercury second sulfide ore is roasted in air when mercury to Nd oxide is formed. When this mercury second oxide is heated to about 300 centigrade, it decomposes, gets reduced, to form mercury metal. Extracting metals in the middle of the activity series. The moderately reactive metals which are in the middle of reactivity series are extracted by the reduction of their oxides with carbon, aluminium, sodium or calcium. Some of the moderately reactive metals occur in nature as oxides, but others occur as their carbonate or sulfide ores. Now, it is easier to obtain metals from their oxides by reduction than from carbonates or sulfides. So, before reduction can be done, the ore must be converted into metal oxide, which can then be reduced. The concentrated ores can be converted into metal oxide by the process of calcination or roasting. The method to be used depends on the nature of the ore. A carbonate ore is converted into oxide by calcination, whereas a sulfide ore is converted into oxide by roasting. Roasting is the process in which a sulfide ore is strongly heated in the presence of air to convert it into metal oxide. For example, zinc occurs as sulfide in zinc blende ore, ZnS. So, in order to extract zinc metal from zinc sulfide, this zinc sulfide has to be converted into zinc oxide first. This is done by roasting. When zinc blende ore, zinc sulfide, is strongly heated in air, roasted, it forms zinc oxide and sulfur dioxide. Calcination is the process in which a carbonate ore is heated strongly in the absence of air to convert it into metal oxide. For example, zinc occurs as zinc carbonate in calamine ore, ZnCO3. So, in order to extract zinc metal from zinc carbonate, this zinc carbonate should be first converted into zinc oxide. This is done by calcination. Thus, when calamine ore, zinc carbonate, is heated strongly in the absence of air, that is, when calamine is calcined, it decomposes to form zinc oxide and carbon dioxide. Extracting metals towards the top of the activity series. The oxides of highly reactive metals, like potassium, sodium, calcium, magnesium, and aluminium, are very stable and cannot be reduced by the most common reducing agent carbon to obtain free metals. This is because these metals have more affinity for oxygen than carbon. So, carbon is unable to remove oxygen from these metal oxides and hence cannot convert them into free metals. Thus, the highly reactive metals cannot be extracted by reducing their oxides with carbon. The highly reactive metals are extracted by the electrolytic reduction of their molten chlorides or oxides. Electrolytic reduction is brought about by passing electric current through the molten salt. This process is called electrolysis. During electrolysis, the negatively charged electrode acts as a powerful reducing agent by supplying electrons to reduce the metal ions into metal. During the electrolysis of molten salts, the metals are always produced at the cathode. This is due to the fact that metal ions are always positively charged and get attracted to the negatively charged electrode, cathode, when electricity is passed through the molten metal salt. Refining of metals. The metals prepared by the various reduction processes usually contain some impurities, so they are impure. The process of purifying impure metals is called refining of metals. Thus, refining of metals means purification of metals. The method to be used for refining an impure metal depends on the nature of metal as well as on the nature of impurities present in it. Different refining methods are used for different metals. The most important and most widely used method for refining impure metals is electrolytic refining. Electrolytic refining. Electrolytic refining means refining by electrolysis. Many metals like copper, zinc, tin, lead, chromium, nickel, silver, and gold are refined electrolytically. For the refining of an impure metal by electrolysis, A thick block of the impure metal is made anode. B. A thin strip of the pure metal is made cathode. C. A water-soluble salt, of the metal to be refined is taken as electrolyte. On passing electric current, impure metal dissolves from the anode and goes into the electrolyte solution, and pure metal from the electrolyte deposits on the cathode. The soluble impurities present in the impure metal go into the solution, whereas the insoluble impurities settle down at the bottom of the anode as anode mud. Let us describe the refining of copper metal by this method. The apparatus consists of an electrolytic tank containing acidified copper sulfate solution as electrolyte. The copper sulfate solution is acidified with dilute sulfuric acid. A thick block of impure copper metal is made anode. It is connected to the positive terminal of the battery, and a thin strip of pure copper metal is made cathode. It is connected to the negative terminal of the battery. On passing electric current, impure copper from the anode dissolves and goes into copper sulfate solution, and pure copper from the copper sulfate solution deposits on cathode. Thus, pure copper metal is produced on the cathode. The soluble impurities go into the solution, whereas insoluble impurities collect below the anode as anode mud.